So today we are going to start the idea of similarity. So first of all, let us define similar matrices. Let A and B be two n by n matrices. We say that A is similar to B and we write A tilde B if there exists an invertible matrix P such that B is equal to P inverse A P, right? So we say that A is similar to B if B and A are connected by this relation. B should be equal to P inverse into A into P. Or we can say PB is equal to AP, right? So first of all, I will prove that similarity is an equivalence relation. So first of all, I will prove that similarity is an equivalence relation. Right? So what we mean by equivalence relation? By equivalence relation, we mean it should be reflexive, it should be symmetric, and it should be transitive. Right? Means, first of all, I will say it should be reflexive. It says that A should be similar to A. Second one, it should be symmetric. It should be symmetric. It means if A is similar to B, then this implies B is similar to A. And the third one, transitive. It means that if A is similar to B and B is similar to C, let us take C, then this implies A is similar to C. First of all, how we can prove that A is similar to A? Since I can write A, I can write A as I inverse A I. I, you know, identity matrix, and I inverse is the same, but I. So I is invertible matrix. Its determinant is 1 and 0, so it is an invertible matrix. So we can say that A is similar to A. Next one, if I take A is similar to B. A is similar to B means by definition there exists an invertible matrix. There exists an invertible matrix, say P, such that B is equal to P inverse AP. Now what I do? I multiply or I pre-multiply P to both sides and post-multiply P inverse. So pre-multiply P, post-multiply P. And here I have P inverse AP, I pre-multiply P and post-multiply P inverse. Now you can see that P and P inverse will become I, and I multiplied with A is A. So I can write A as P inverse. And you know that in matrix theory, inverse of A inverse is A. Inverse of A inverse is A. So I write P as inverse of P inverse B into P inverse. Now I take P inverse as K. So this is K inverse B K. Right? Therefore, B is similar to A because P is invertible. So K is also invertible. Hence, we have proved that B is similar to A. Now, what I assume? See, I assume that A is similar to B and B is similar to C. So A is similar to B, B is similar to C. So by definition, this implies that there exist invertible matrices. There exist invertible matrices, say P and Q, such that, now see here, A is similar to B means B equal to P inverse AP, and now B is similar to C means C is equal to Q inverse B Q. Now what I have to show, see, I have to show that A is similar to C. I have to show that A is similar to C. So now, what is C? C is Q inverse B Q, right? And Q inverse B, B is P inverse AP. I write P inverse AP and Q. Now, what is Q inverse into P inverse? You know that matrices satisfy Sous-of property, means AB inverse is nothing but B inverse into A inverse. So I write this as PQ inverse then A then PQ. I take PQ as K, so it becomes K inverse AQ. So A is similar to C. From what has been done, from it is clear that A is similar to C. So all the three properties, reflectivity, symmetry, transitivity, are satisfied. So similarity is an equivalent relation. Next. So now we have to look for the properties which are shared amongst similar matrices. We have to look at the properties which are shared amongst similar matrices. So I record this in the form of theorem. So theorem is, let A and B be n by n matrices with A similar to B. Then, see, first property is that determinant of A will be equal to determinant of B. Means similar matrices have the same determinant. Similar matrices have the same determinant. So let us prove it. A is similar to B. It is given that A is similar to B. This means, by definition, there exists an invertible matrix, call it P or anything, call it P, such that B is equal to P inverse A P. Now, what is determinant of B? What is determinant of B? This is determinant of P inverse A P. Now, what is this? This is determinant of P inverse into determinant of A into determinant of P. And what is determinant of P inverse? It is 1 by determinant of P into determinant of A into determinant of P. I cancel this 2. So this is equal to determinant of A. Right. So similar matrices have the same determinant. Let us jump into the next property. See, once we prove this theorem, what can be done more? See, I am writing second property here because it can be derived from the first one. See, if A is invertible, if and only if B is invertible, B is invertible, right? A is invertible if and only if B is invertible. See, A is invertible means determinant of A is not equal to 0. Now, if A and B are similar, then determinant of A is equal to determinant of B. That's why if determinant of A is not 0, determinant of B is not 0. So if determinant of B is not 0, B is invertible. In the same way, we can proceed back. If B is invertible, then determinant of B is not equal to 0. Now, determinant of A and determinant of B are equal, so determinant of A cannot be 0, and hence A is also invertible. So, because this condition, invertibility, depends on non-zero determinant, and because they have the same determinant, so if one is invertible, another one is invertible. Okay, let's jump into the next property. Third one, C is A and B have the same rank. The same rank. So this property is crucial. This property, this property is crucial. See, A and B have the same rank. So how we can prove this? Because this requires some exercises to be performed. See, suppose U is invertible. I write, if U is invertible, Then what about the rank of A? The rank of A will be equal to the rank of UA, right? And what about the rank of UA? This is equal to rank of AU. In the case of invertible matrices, it is if U is invertible, then we have this inequality, and we are going to use this one. Now, A is similar to B, then this implies there exists invertible matrices. There exists invertible matrix P such that B is equal to P inverse AP. Right? Now, what is the rank of B? What is the rank of B? The rank of B is the rank of P inverse AP. And now, what about P? P is invertible matrix. So I can write this as the rank of P inverse into AP. I apply the property above. This is nothing but rank of AP only. Again, I apply the property mentioned above, that is equal to rank of A. Right? So I apply 2 times the property which I mentioned. And using that, I can prove that 2 similar matrices have the same rank. Is it clear to all of you? Is it clear? Am I audible?
Yes, sir.
Is it clear?
Yes, sir.
Yes. So let's jump on the other property. Now, I will prove here couple of properties. D, A and B have the same characteristic polynomial. A and B have the same characteristic polynomial. Right? So how we can prove this? See, if A is similar to B, I write the same line. There exists an invertible matrix P such that B is equal to P inverse AP. Now, what is here? Characteristic polynomial of B, that is determinant of B minus lambda I. This is the characteristic polynomial of B. So what I do here, B is nothing but P inverse AP. So I write determinant of P inverse AP minus lambda I. Now what I do, I will write as P inverse into P. So determinant of P inverse AP minus lambda I write as P inverse P. Now it's simple. So determinant of I write P inverse A minus lambda I, and again I take P common this. Right. So this is nothing but determinant of P inverse into determinant of A minus lambda I, because determinant of A into B is equal to determinant of A into determinant of B into determinant of P. And now what is determinant of P inverse? This is 1 by determinant of P into determinant of A minus lambda I into determinant of P. So this I cancel. So I am left with determinant of A minus lambda I. Okay. So characteristic polynomial of A and characteristic polynomial of B are same. And with this, I can add another property because they have the same characteristic polynomial. So, and roots of the characteristic polynomials are eigenvalues. So, A and B will also have the same eigenvalues. So, if A is similar to B, then A and B have the same eigenvalues. Same eigenvalues. Okay, let's jump into next property. Now, see, if A is similar to B, then this implies A to the power m is similar to B to the power m for all positive integer m. Positive integer m. Now, it can be proved easily. See, if A is similar to B, then there exists an invertible matrix P such that B is equal to P inverse A. Now, what is B square? See, what is B square? It is P inverse AP into P inverse AP. So, you can see in the middle, P and P inverse are getting cancelled. It is equal to I, and so A into A is A square. So, it is P inverse A square P. So, what does this shows? This shows that A square is similar to B square. Again, what is BQ? This I can write B square into B, and B square is P inverse A square P into B. B is P inverse A P. Again, in the middle, P and P inverse, that is I, and A square into A is AQ. So I write P inverse AQ into P. So this is AQ is similar to BQ. And in the same way, I can prove that A to the power m is similar to B to the power m for any positive integer m. So for all positive integer m. Is it clear to all of you?
Yes, sir.
Yes, sir. Now, what is EFG? What is G? See, they have the same trace. Means if A is similar to B, then this implies trace of A should be equal to trace of B. What do you mean by trace of A? What do you mean by trace of A?
Sum of leading diagonals.
Sum of leading diagonal elements. All right. Sum of leading diagonal. So I can prove it again in a simple manner. So see, because we know that for n by n matrices, for n by n matrices, right? Trace of AB is equal to trace of BA. See, this is only applicable to n by n matrices. If they are not of the same order, then it may not be a valid result, right? Because if you take A as 2 by 3 and B as 3 by 5, then BA will not be defined. So we can't have equal trace. Even trace is not defined, right? So this property is only applicable when both A and B are n by n matrices. Now what we have, I have A is similar to B, then this implies B is equal to P inverse AP for some invertible matrix P. For some invertible matrix P. Now, see, trace of B, right? Trace of B is nothing but trace of P inverse AP, right? Now what I do, I club these two elements together and this two. This I read as A, this I read as B. So AB is equal to BA. Trace of AB is equal to trace of BA. So this is trace of AP into P inverse. Now P and P inverse is getting cancelled, so this is equal to trace of A. Right? So if A is similar to B, then trace of A is equal to trace of B. Next property, this is G, this is H. If A is similar to B, then this implies A transpose is similar to B transpose. Right? If A is similar to B, then A transpose is equal to B transpose. So I am going to use here the second one, second definition. What was that? See, A is similar to B. This means that there exists an invertible matrix P such that B is equal to P inverse AP. Or equivalently, I can say that P into B is equal to A into P. Right? Equivalently. So I am using this one. I am using this one. Now, PB is equal to AP. So I take transpose. And you know, again, AB transpose is equal to B transpose A transpose. B transpose A transpose. So I apply this. So this is equal to, this is equal to B transpose P transpose, and here AP transpose, so it is P transpose A transpose. So what this means? This means A transpose is similar to B transpose. I am using only this definition. Right? You can see A is similar to B, so A P is equal to P. Right? Same type I am doing. Next property is that or diagonalization is not in your syllabus, so one more property I can do. My question is, if A and B are invertible matrices, are invertible matrices, right? A and B are invertible matrices. Then so that AB and BA are similar. AB and BA are similar. Now see what I have to show. AB and BA are similar. So I start with BA. I start with BA. Right. So what I do, BA with A, I need B, I supply B, and in order to cancel this, I put B inverse. So what is this? This is B into AB into B inverse. So B, how I can write B? B is inverse of B inverse into AB into B inverse. I take B inverse as K, so it is K inverse AB into K, where K is B inverse. From this, AB is similar to BA. Right? From this, AB is similar to B. Alright, so these are the properties associated with similarity. Now, shall we solve some problems related to this similarity? All of you, you understood this thing?
Yes, sir.
Yes, sir. Okay. So let us start how these properties help us in problem solving. That is important because knowing property means you don't know anything. You have to apply properties in problem solving. So first of all, how these properties help. See here, so that so that A and B, A and B are not similar matrices, are not similar matrices, right? My first question is A is 4131 and B is 1001. So how we can show this thing? See what I have done. I have done A is similar to B implies determinant of A should be equal to determinant of B. I take this as statement P. I take this as statement Q. So I have statement P implies Q. So what will be the negation of that? See, the same statement can be written as not Q implies not P. Right? Means if determinant of A is equal to determinant of B, this is Q. So not equal to, this is means not Q will imply not P. P is A is similar to B, not P is A is not similar to B. Right? So see, actually in local languages you can understand if it rains, I will go to school. Right? Not this, I will not go to school. If it does not rain. Look at the statement. Right, these two are same statements. They have the same truth value. When you calculate truth value, it has the same truth value. You calculate truth value of P implies Q. You calculate truth value of not Q implies not P. You will get the same thing. Right? So what I am doing here, see, we have to show that A and B are not similar matrices. So A and B are not similar matrices. If you want to show, then what you do? Either you prove determinant of A is not equal to determinant of B, right? Or you prove they don't have the same characteristic polynomial, or you prove they don't have the same trace, or you prove they, their eigenvalues are different, right? So any of the properties you disprove and your work will be done, right? So what I do here, let us take the help of characteristic polynomial. Let us take the help of characteristic polynomial. Right. So first of all, I calculate characteristic polynomial of A. See, characteristic polynomial of A. What is this? 4 minus lambda, 1, 3, 1 minus lambda. Determinant. So it is 4 minus lambda into 1 minus lambda minus 3 1 is 3. So this is minus lambda into minus lambda, lambda square, minus 4 lambda minus 1 lambda minus 5 lambda, 4 into 1 4 minus 3, that is 1. So this is the characteristic polynomial of A. Similarly, you go for the characteristic polynomial of B. Characteristic polynomial of B. What is B? You can see here determinant of 1 minus lambda 0, 0, 1 minus lambda. So it is simple 1 minus lambda whole square. So you can see easily that they don't have the same characteristic polynomial. Therefore, A is not similar to B. What is the other way? You look at the trace of A. 5, 2, their trace are not equal. So they are not similar. Right? Let us jump into the next question. A is 1, 2, 0, 0, 1, minus 1, 0, minus 1, 1. Right? And what is B? B is 2, 1, 1, 0, 1, 0, and 2, 0. Right? What you can do? What you can do? See, their trace are not equal. Simple. If you want to go in a simple way, then you can see that their trace are not equal. Otherwise, you compute characteristic polynomial of A and characteristic polynomial of B. So they will not have the same characteristic polynomial. Their characteristic polynomials are unequal, and hence A and B are not similar. Similarly, where eigenvalues help, see here, eigenvalues help where, suppose I write A 2, 1, 4, 0, 2, 3, 0, 0, and B is 1 0 0 minus 1 4 0 2 3 4. Now, what you can say this one? What are the eigenvalues? Tell me. What are the eigenvalues of A? Tell me, what are the eigenvalues of A? See, what is A? Look at the entry. A is triangular matrix. So, eigenvalues are just the elements on the diagonal. And same is happening. B is also triangular matrix. So, eigenvalues are the diagonal elements. So, you observe that the eigenvalues of A and eigenvalues of B are different. Therefore, A is not similar to B. That's all. This is the advantage, right? You don't have to compute determinant. You don't have to compute eigen uh, uh, characteristic polynomial. You don't have to go for the trace. Nothing. Is it okay? Is it okay?
Yes,
Am
sir.
I audible?
Could you show, sir, one C property, sir? Property third.
A, B, C. Yeah, this is.
Okay, sir. Got it, sir.
Okay.
Okay, sir.
Now, next question is how you can solve. This is only related to the case where you have to show that A and B are not similar, right? When you have to show that A and B are not similar. But suppose anyhow you have to show that A and B are similar. Suppose you have to show that A and B are similar. Then how you will show? You have to you have to show you have to show the existence of invertible matrices. You have to show the existence of invertible matrices. So let us take one question and then I will finish the class. So see, my question is matrix A given by 1, 2, 4, 3 similar to B which is given by 5, 0, 0 minus 1. See, here you have to show how A and B are similar. So, what I do, let us construct F as X, Y, Z, T. Now, see, A and B will be similar if AF is equal to SB, where X should be some invertible matrix, right? So, see, A is 1, 2, 4, 3 into S. S is X, Y, Z, T. This is equal to X, Y, Z, T into B. B is 5, 0, 0 minus 1. Right? Now, let us multiply. Now we multiply, so x plus 2z, x plus 2z, y plus 2t, and 4x plus 3z, and 4y plus 3t. Multiply the right hand side. This is 5x, y into 0, x into 0 minus y, and then 5z and 0 minus t. So see, these two matrices will be equal if their corresponding components are equal. Means x plus 2z is equal to 5x. So I write x plus 2z is equal to 5x. So 5x minus x 4x. So 2z is equal to 4x. I cancel 2 from the both sides. So z is equal to 2. Right? If z is equal to 2x. This is the one. And next, y plus 2t should be equal to minus y. So I write y plus 2t is equal to minus y. Right? So I take y to this side. So 2t is equal to minus 2y. Or from this, I will get t is equal to minus. So this is the second information. So now I am able to construct f. F is what? X, y, z. Z is my 2x. Z is 2x. And then t is minus 1. So this is mine. Now, question is whether s is invertible or not. So first of all, I calculate determinant. Determinant of s. So this is minus xy minus 2xy minus 3xy. Now you can see determinant of s not equal to 0. Determinant of s not equal to 0 implies that x should be different from 0 and y should be different from 0. Right? If and only if. Right? So now you can see what simple values you can take. I take x is equal to 1, y equal to 1. Take the simplest value 1, 1. So what is s? S is 1, 1, 2 minus 1. And you look, this determinant is not equal to 0. Therefore, A is similar to B. Therefore, A is similar to B. All right. Is there any question? Any confusion?
No, sir.
Okay. Okay, then I am stopping this class. Later on, there is lots of things with similar matrices. So first of all, you have to be very careful while using its role in change of basis, because from change of basis the idea of similarity will arise. And second role of this is in diagonalization. You know how to diagonalize a matrix. S inverse AS is equal to lambda. S, how you construct? S you construct by taking eigenvectors as columns, by taking linearly independent eigenvectors as columns. So S inverse AS, again you can see similarity is appearing. So you have to take this concept in change of basis and diagonalization. Then it will be a complete formation. So, okay, thank you. If you have any query, you can ask me anything. Okay, thank you.